as we advanced forward with technology. Our sole purpose is to make this world closer and faster. As time is of the essence, saving time is either a luxury or a necessity. In this world, every minute counts. Even a second can change a life. It takes an ambulance 18 minutes on average to arrive to the emergency scene. Victims with critical conditions suffer from this delay. A study shows that 9 out of 10 cases of cardiac arrest lose their lives due to the absence of immediate help. To this problem, we present by sending a flying drone to the emergency scene. Delivering the most needed device, the automated external defibrillator. The bystander will be guided through the integrated speaker on the drone. This increases the chances of resuscitation from 6 to 67%.
In order to fly a drone, we need to produce an upward force. This force is provided by rotors and propellers. We use brushless motor to provide this force. A brushless motor has 3 wires.
By activating 2 different lines respectively, the rotor rotates to a different angle.
And this rotation is controlled using an electronic speed controller. An ESC converts DC power coming from the battery to AC power going to the motor. The speed of the rotor is controlled through a PWM signal from the microcontroller, which means we need 4 ESCs, 1 for each motor. A rotating propeller produces the required thrust force, introducing a torque which causes the body to rotate in the opposite direction. For each rotor rotating clockwise, we need another rotor rotating anti-clockwise, so that the net torque is equal to 0. In addition to moving with the required speed in different conditions. So we use the professional calculator, which takes in all the characteristics of the components and gives us the estimated flight results, such as the flight time, power dissipation, and the thrust.
Alongside the mechanical components that allows the drone to generate lift and maneuver in mid-air, drones also employ an array of sensors that constantly collect information from their surroundings. With this information, drones can maintain their positions, determine how fast they are, and avoid obstacles. In order to fly the drone autonomously, we need to know its acceleration and its orientation. To do that, we need a couple of sensors. The GPS module is the one responsible for providing the drone with its current coordinates. The principle behind GPS technology is pretty simple. A drone is mounted with a GPS receiver that can receive signals from several GPS satellites. The accuracy of the location will depend on the strength of the signal and the number of satellites within its range. In order for the drone to fly autonomously, the drone should identify a heading using a magnetometer. As its name implies, a magnetometer measures the strength and direction of a magnetic field. Using this principle, a drone can always determine the direction of the magnetic North Pole and adjust its trajectory accordingly. To measure the acceleration and orientation, we need an inertial measurement unit. This unit consists of gyroscope, accelerometer, and magnetometer. Gyroscope is a sensor used for measuring orientation, while the accelerometer determines the speed of the drone, working together to determine changes in its position and orientation. This helps in collecting information of the drone's roll, pitch, and yaw, and feeding back this information to the PID controller.
Standalone sensors can do the job alone due to either it's prone to drift or its measurements are noisy. Depending on them, will cause the drone to be unstable. We need a way to estimate measurements from these sensors. The best approach for estimation is through base filters, and the one we used in this project is the extended Kalman filter that deals with nonlinear equations, which we have in our case. The extended Kalman filter, for example, takes the position values that we got through integration of accelerometer measurements that's prone to drift, and the direct position values using GPS modules that are inaccurate, and decides based on previous estimation which sensor should be trusted more, and estimate values closer to it. But as the information we need to know increases, the math gets harder to implement. We are going to get the angular body velocities directly from the gyroscope. Also the roll and pitch angles we are going to estimate using a complementary filter. As we can see here, the accelerometer measurements are much more noisy, while the gyroscope accumulates error, which makes depending on either of them insufficient. Therefore, combining both measurements, we get a much more accurate results.
And now that we know how a drone flies and how it senses its surroundings, it's time to know how to actually control a drone. To have a better intuition, let's take an example of a drone moving along a single axis. If a drone was to move from point A to point B, it would have to generate a thrust proportional to the difference in distance. However, depending on this concept alone is not enough, as it will result in the drone overshooting beyond the target location. Due to this overshoot, a new difference in distance will be introduced, which will force the drone to go back to its target location and yet miss it, resulting in an unwanted oscillatory movement around the target location. What we need is a controller that will actually stabilize the drone at the target location. Such a controller is called a PID controller, which takes into consideration the covered distance and the change in velocity to adjust itself accordingly. Eventually, the controller will look something like this. The pink lines are the feedback coming from the sensors through the Kalman filter, while the gray lines are the input target location and orientation. Together with the pink lines, they go through each block and producing the yellow output lines. These blocks together give out the required values of forces that each motor needs to get to the required destination.
After determining the shortest path from the location of the drone to the location of the patient, we take the in-between obstacles into our consideration to guarantee safe arrival of the drone to the patient as fast as possible. Many obstacle avoidance systems were done by using sensors, but we used more accurate and reliable system which based on using of single camera and deep learning model to ensure early detection and avoidance of any obstacle. We used a camera and 4G to send live video streaming to the server in real time to ensure fast response of the drone toward any nearby obstacles. When the video streaming reaches the server, YOLO algorithm is used to analyze the video searching for any obstacle and send the feedback to the drone. We have trained YOLO model to detect the obstacles as well as guessing the distance between the drone and any obstacle, which helped the drone in taking the suitable action. Upon receiving the feedback from the server, the drone begins immediately to take precautionary actions to avoid possible collisions.
By achieving this, we enable everything to be connected with less and less human interaction. Following the Industry 4.0, the drone can answer to emergency calls by simply receiving the coordinates of the emergency scene, or it can be by an application, or through the hospital, or any nearby device. Since our project depends entirely on 4G, it can be argued that it might have a slow response. However, since 5G is just around the corner, we will not be facing this issue. If such idea is brought to life, it opens the doors to numerous kinds of applications that depend on the same concept, such as delivering medical kits to rural areas to boost healthcare access, or can be used in firefighting to detect the kind of fire being dealt with. In a nutshell, drones will shape our future into a much better world, and it's an honor to be a part of it. Thank you for watching.